Hi, I'm Zor. Welcome to Unizor Education. I would like to remind you that trigonometry was called trigonometry because it helps to solve different problems about triangles, right? I mean, that was the original purpose of trigonometry. So, after all these lectures about the properties of trigonometric functions, etc., well, let's try to do something which trigonometry was supposed to do, which is just solve a few problems related to geometry of triangles. Well, first of all, to state these problems, I will need certain symbols. So let me just introduce some standard which I will try to adhere to wherever possible. And I think it's a good standard to call the same elements of the triangle with similar letters, and I do recommend you to do exactly the same. So the way how I will use the symbols is the following. So if I have a triangle, my usual way of calling the vertices is with capital Latin letters. Now the sides will be called with the corresponding lowercase letters. The side which is opposite to vertex A will be called lowercase a, lowercase b, lowercase c, and the angles I will also use the sequence of the similar letters in Greek alphabet, which is alpha, beta, and gamma. Now, next, there are different elements of the triangle which I will also use. Now, these are, well, the first three major elements are median, angle bisector, and altitude. So, if this is an altitude, I will usually call it HA, the length of this altitude. Now, if H because it's the height basically, and A because it falls on the side called A. Now the median, let's say the median from the vertex B, it goes to the middle of this. The length of this median I will call lowercase m with, oh, I'm sorry, it's on the B side, so it would be B, the suffix B. So the median is MB, correspondingly MA or MC, and the altitude is also, this is HA, and obviously this would be HB and this would be HC. And now the angle bisector, let's say the angle bisector of this, I will use the letter lowercase l, and in this case suffix will be C because it falls on the side C. The radius of circumscribed circle, I will use letter R, and inscribed lowercase r. Well, sometimes it's written like this, whatever you prefer. I prefer this. And other elements I will basically introduce on the ongoing basis. But these are standards which I would like to state once, and then I can basically present the problem something like this. And this would be the first problem which I'm going to solve today, is this one. Prove that in any triangle, A minus B times A plus B times sine gamma equals to C squared sine A minus B. Oh, sorry, alpha minus beta. Now, what does it mean? Well, obviously A and B are two sides. C is the third side. Gamma is an angle which is opposite to the vertex C, and alpha and beta are angles opposite to vertices A and B correspondingly. So that's what I would like to prove. Now, there are already a couple of things which I have mentioned in the previous lecture, one of the previous lectures. the law of sine and law of cosine. Now, you remember, if you don't, then go to the corresponding lectures, that the law of sine is this. And again, I'm using my symbolics, which I have just introduced. This is law of sines. Now, I think it was one of the lectures in the trigonometric identities chapter. So go to unizor.com, and in the trigonometric identities you will find the lecture which is devoted to the law of sines. And there is another one which is devoted to the law of cosines. So these two, the law of sines and the law of cosines, square of any side is equal to sum of the squares of other two sides minus double their product and cosine of the angle between them. So these two actually are the first usages of the trigonometry in the geometry of the triangles. And I will definitely use these two laws, these two theorems, which I have proven in that other lecture which I just mentioned to you, to solve this problem. So how can I, using this particular law of sines, because it looks like this is a sine, this is a sine, it looks like law of sines should be used in this case. How can I do it to prove this particular equation? Well, using the law of sines, I can express A in terms of C and sine of alpha and sine of gamma, right? C sine of alpha divided by sine of gamma, right? And similarly B. It's sine of beta divided by sine of gamma. Now, using this, I can substitute it in these cases, and that would basically transform my original equation, which I have to prove, into something simpler, obviously, because there is no extra variables here. Now, also, I have to mention another interesting property. Now, you know that the sum of angles in any triangle is 180 degrees, right? Pi. So, sine of gamma is equal to sine of pi minus alpha minus beta. Let me write it differently, right? Which is the same thing. Now, what is a sine? Sine is, as you remember, is ordinate of the point on the unit circle. This vertical thing is ordinate. And obviously, if this is some kind of angle phi, this would be angle now if you count in this way, it also would be phi, right? Now this angle it's pi minus phi, right? And the ordinates are obviously the same. We proved in many cases that the sine of pi minus some angle is equal to sine of this angle. So that's another thing which I'm going to use instead of sine of gamma. So all the left part I will express in terms of C, sine alpha, and again instead of sine gamma I will use sine of alpha plus beta. So all will be in terms of C, alpha, and beta. And let's see if I will get an identity in this case, because everything else seems to be just dependent on these three variables of two angles and the side. Geometrically, by the way, it's worth mentioning that if this is C, this is alpha, and this is beta, this is gamma, this is A, B, and C, right? So you know that triangle can be constructed using some three elements, like for instance a side and two angles which are adjacent to this side, right? So that's actually three independent elements which basically define a triangle. So it's not a surprise that I will need exactly 3 elements to express all other elements. So I need alpha, beta, and c to express all other elements in terms of these elements. So that's what I'm going to do. I will take 3 independent variables, in this case c, alpha, and beta, and express everything in these terms, and then see if I will get an identity. Now, this expression is invariant. I don't lose any specific values because it's a triangle, which means none of the angle is equal to 0, and all angles are less than pi, right? So it has geometric sense in this case. It's a triangle. So there is nothing wrong with dividing by sine of gamma. It cannot be equal to 0. So this is an invariant transformation. So that's what I'm going to do. I'll substitute it over there. And here is what I have. Okay. Alpha minus beta and alpha plus beta. Well, obviously, c over sine of gamma, I can take out, factor out of the parentheses, and I will have c divided by sine of gamma, which now I will replace with sine of alpha plus beta, as you know, right? Since alpha plus beta is pi minus gamma, or gamma is equal to pi minus alpha plus beta, and sines are the same. Inside I will have sine alpha minus sine beta times sine alpha plus sine beta. Now, since I have a and b here, and a and b here, it would be square and it would be square, right? So sine of alpha over gamma would be from a, and I mean c over sine of gamma would be from a, and c over sine of gamma would be from b, and these I take out of the parentheses, and these guys have exactly the same thing. So I have the c square and c square and sine square. So that's on the left. And sine of gamma, which is basically another sine of alpha plus beta, so I can just completely wipe out this square, right? That would be fine too. So this is my left part. After I substituted, instead of sine of gamma, sine of alpha plus beta, and instead of a and b, I substitute these values. That would be on the left. Now, sine of alpha plus beta, again, is not equal to 0, because it's exactly the same as the sine of the third angle, gamma, which is not equal to 0. So everything is fine, everything has meaning. Okay, so I have to prove that this is equal to c squared sine of alpha minus beta. Okay, how can I prove that? Well, obviously I can reduce this c squared. It's not equal to 0, so no problem. And they have only trigonometric expression which I have to prove, trigonometric equality which I have to prove. So is this an identity with any angles alpha and beta from 0 to pi? Not equal to 0, not equal to pi. Well, obviously we can multiply both sides by sine of alpha plus beta, and it will be here. So identity which I have to prove is this one. Now, I multiply sine minus sine and sine plus sine as sine square minus sine square, right? You know, that x minus y times x plus y is x square minus y square, right? So I have this on the left. On the right, I have sine of alpha minus beta times sine of alpha plus beta, right? So this is sine alpha cosine beta minus cosine alpha sine beta. That's this one. And this one would do the same thing with a plus. So again, I have x minus y and x plus y. So it's basically x squared minus y squared. That would be on the right. Well, obviously I have to replace cosine beta with 1 minus sine. So I will have everything, and cosine alpha was 1 minus sine. So I will have on the right sine square alpha times 1 minus sine square beta minus sine square beta. Now, instead of cosine square, I will have 1 minus sine square alpha. So what exactly? Now, the left part is the same. Now, here I have sine square times 1, which is sine square alpha, minus sine square alpha sine square beta, minus sine square beta. And now minus is minus, it would be plus sine square alpha and sine square beta. As you see, this is reducible, and I have sine square minus sine square, exactly what I have to prove. And these all invariant transformations, so it goes both ways without any problems, and that's the end of the proof to the first problem. So what I did use here is a theorem which is called the law of sines. It helped me to express all elements of the triangle involved in this particular problem through 3 independent variables. And in this case, it's one side, which is C, and 2 angles adjacent to this side. And then basically everything else is technicality. Next problem. Okay, express A, B, and C in terms of R, alpha, beta, and gamma. R is the radius of circumscribed circle, and alpha, beta, and gamma are angles, obviously. Okay, so if you have a circumscribed circle around the triangle, A, B, C, alpha, beta, gamma. This is the center. So let's use this one. So this is R, this is R, and this is R. Okay? Now, look at this. Angle beta is supported by this arc, right? Angle AOC is a central angle, which is supported by the same arc. So this is inscribed angle, this is the center angle, and you know that the center angle is twice as much as the inscribed angle, right? So angle AOC is equal to 2 beta. This is 2 beta. Now, correspondingly, this is 2 gamma and this is 2 alpha, obviously, for the same reason. Now, if I draw a perpendicular from the center to a point M, which is middle of the AC, now this perpendicular would obviously divide my isosceles triangle AOC into 2 rectangle, into 2 right triangles, sorry, because this is perpendicular, right? So these are right angles. So my isosceles triangle, by an altitude from the top, would be divided into 2 right triangles, obviously congruent to each other. Well, because the sides are the same and the hypotenuses are the same and the catetus is common, they're sharing it. So, angle AOM is half of the angle AOC, so this is beta and this is beta, right? Now, and AM is obviously half of AC. So, angle AOM is equal to beta, and AN is equal to half of B, right? This is the side B, lowercase b, opposite to the vertex B. Well, obviously, we can calculate the lengths of AM in terms of hypotenuse and an angle using the definition of the sine in this case. So obviously, AM divided by AO is a sine of beta. So AM, which is 1/2 B, is equal to hypotenuse, which is R, times sine of this angle AOM, which is beta. From here, B is equal to 2R sine beta. And very similarly, obviously, A is equal to 2R sine alpha, and C is equal to 2R sine gamma. Exactly the same logic can be in this triangle or in this triangle. So this is how the sides are expressed in terms of radius of the circumscribed circle and angles. Now, let me go back to the law of sines. Law of sines says that A over sine of alpha is equal to B over sine of beta equal to C over sine of gamma. Now I can put equals to 2R, right? So this ratio, which we had established before as being the same for all three sides and all three angles, is not just some abstract number, whatever that number might be, God knows what it is. It's basically a diameter. 2R is a diameter of a circumscribed circle. So it has a geometric sense. So any side divided by a sine of the opposite angle gives you the diameter of the circumscribed circle. That's actually an interesting, kind of unexpected geometrical interpretation of this ratio. Okay, next. Well, I usually mention it at the very beginning of every lecture, but let me mention it in the middle. Most of the problems which I'm presenting to you don't make any kind of a practical interpretation or sense or anything like that. They are only for your exercise of your ingenuity, your creativity, and basically ability to solve something which you have not really faced before. So again, I'm categorically against the education when the teacher is saying, okay, this is the problem, this is the solution, use it wherever you can, because most of these problems will never be occurring in the real practice. It's important for you to make some kind of a way to solve the problem. So that's why I'm always encouraging you, before you're listening to the lectures which I'm presenting here, try to solve these problems yourself. That's very, very important. That's the most important, actually. Because if you don't, if you just listen to these lectures without trying to solve something yourself, it's basically useless. Okay, now, another problem. Here is your triangle. And here are three altitudes. Let's call this point H. Now, what's necessary to solve, to prove actually, that radiuses of circumscribed circles around triangles AHC, triangle BHC, and triangle AHB. So AHC triangle, BHC triangle, and AHB triangle. So these three triangles have the same radius of a circumscribed circle. But it's obviously not, just looking at the picture you don't see it. So one circle would be, something like this, another would be here, and the third one would be there. Why are they supposed to have the same radius? It's not obvious at all. However, let's just think about it. Now, these are perpendiculars, right? Now let's consider, let's say, M and P. Okay. Let's consider a triangle BNH and triangle APH. So this triangle and this triangle. Okay? Now, obviously these angles are vertical. These angles are right. So these angles are equal to each other. So angle HBC equals HAC. So this angle is equal to this angle. Now, let's consider now a triangle BHC, this one, and triangle AHC, and this one. These two triangles. So it's this and this. These are two triangles which I have to prove this property that the radius of the circumscribed circle is the same. Now, they share the side HC, right? And these triangles have the angle opposite to this side. Opposite to HC in this triangle is this, and opposite to the same side but in this triangle is this, and the angles are the same. Now, we just proved in the previous problem, you remember, A is equal to 2r times sine of alpha for a triangle, right? Alpha is an opposite angle to A. Now, applied to these two triangles, this would play the role of A. This is this side. In this triangle, the opposite angle is this. In this triangle, opposite angle is that. And they're the same. So the side is shared, and the angles, opposite angles are the same. And that's why, considering this formula, I have to have, so A is the same and sine is the same, so R is supposed to be the same. So that's why R for both these triangles are the same, the radiuses of circumscribed circle, because it's expressed in terms of this. Side is shared and angles are the same. That's why the radiuses are the same. That's it. And the last problem, which I would like to present in this introductory lecture about trigonometry applied to geometric properties of the triangle, is how to express the area of a triangle in terms of radius of a circumscribed circle and angles. So I have angles, three angles, and I have radius. Well, this is easy. Again, let's connect these guys. So, as before, if this is an angle beta, this is an angle beta. Because this is the half of the central angle, which is supported by the same arc as this inscribed angle. Similarly here, if this is gamma, then this is gamma as well, and this obviously. And this is alpha. Okay? Now, the area of a triangle can be now divided into 6 small triangles, right? And pairs are exactly the same. And this is the right triangle. Each one of them is the right triangle. What do I know about this right triangle? I know hypotenuse, which is r. In all cases, hypotenuses are r. And I know the angles, basically. This angle. And angle is enough. With a hypotenuse, angle is enough to determine both categories, right? So, for instance, the triangle MNOP, triangle AOM has area, this catetus times this catetus divided by 2, right? If this is r, and this is beta, then one catetus is r sine beta, another is r cosine beta, and divided by 2. That's the area of one triangle, right? Now, the area of another triangle is exactly the same. So both of them together have this area, right? This is AOC now. Similarly, for a triangle BOC, I have r sine alpha times r cosine alpha, and for triangle AOB, I have r sine gamma, r cosine gamma. Now, total area, I have to sum them together, which is r squared times sine, cosine, sine, cosine, sine, cosine. What is sine times cosine of an angle? You remember that sine of 2 phi is equal to 2 sine phi cosine of phi, right? So sine times cosine is half of the sine of a double angle. So I will put 1/2 in front of it, and instead of sine cosine alpha, I will put sine of 2 alpha plus sine of 2 beta plus sine of 2 gamma. So that's the formula. This is total area. By the way, I'm using the letter S for area. You can add this to all the other symbolics which I'm going to use. I would like to use it more or less wherever I can. So that's the result of expressing the area of a triangle in terms of the radius of circumscribed circle and angles. Now, there are many more problems in the same category which I'm going to present you. I'm not sure present many problems, but as much as I can. And all of them, they are very, very educational quality. So I'm encouraging you as much as I can to spend some time and try to solve these problems yourself. They are very educational, so to speak. They are very well in developing your ingenuity and creativity. So all the subsequent lectures in this particular chapter of the course related to trigonometry and geometry together, all of them are very, very important for you to be able to solve yourself. Now, after this lecture is completed, try to basically to do exactly the same with these problems. So it would just, kind of remind you exactly how it can be solved if you didn't do it yourself before. As everything else, this lecture is on unizor.com, which you are welcome to visit this site. And what's important is if you register with this website, and there is also some supervisor or your parent actually registered as a supervisor for you, then you will be able to take exam. Your supervisor, your parent, will be able to enroll you in different topics, so you will be able to go through exam, and you will see the results of your education yourself by basically checking the score on the exam. And exams can be just taken any number of times. Don't worry about that. The site is completely free, so everything is available. Basically, that's it for today. Thank you very much, and I'll try to put as many other problems in the future lectures. Thank you. Goodbye. Hi, I'm Zor. Welcome to Unizor Education. I would like to continue solving problems related to usage of trigonometry in geometry. So it's geometrical problems, but a big part of it is supposed to be using the trigonometry. There are many problems, so I'm sure I will not cover everything. However, I'm trying to put together some material, some educational material, which should be relatively universal as far as different aspects of trigonometry is concerned. So, here are these problems. If you did not spend any time solving them yourself, just using the unizor.com, this is the set of problems number 1 in the trigonometric geometry chapter. So if you didn't do anything just by yourself, I do recommend you just to pause this particular video and spend time trying to solve these problems yourself. They're very helpful, educational, they develop your creativity, your intelligence, so it's definitely a must. Because if you don't do anything yourself, if you just consume information which I'm presenting, then the usefulness of these lessons is really limited. Anyway, so let's just solve all these problems. Where is my... okay, here it is. Okay. Problem number 1. Prove that in any triangle AB, sine square of gamma over 2 equals to P minus A, P minus B. Now, I'm using the symbolics which are introduced in the previous lecture, and basically A, B, and C are sides of the triangle, which lie opposite to vertices which are similarly called by using the capital letters. Now the angles are alpha, beta, and gamma, again alphabetically, and lowercase p is half the perimeter. So that's the abbreviation, that's the symbolics which I'm using here, and I will try to use it more or less universally. So we have to prove that in any triangle this is true. Well, what am I thinking about the approach to solve this particular problem? First of all, nobody likes something in square if there is some way to bring down the power to 1. And there is a way, actually. Remember, cosine of 2 phi equals to cosine square phi minus sine square phi. Or, if we express cosine square as 1 minus sine square, it will be 1 minus 2 sine square phi, from which I can solve sine square phi is equal to 1 minus cosine 2 phi over 2, right? So I'm going to use this formula to convert sine square of gamma over 2. Now phi is gamma over 2, so it's 1 minus cosine of double angle, which is gamma, over 2. That's something which looks much simpler, right? So I will substitute it over there and see what happens. So 1 minus cosine gamma over 2 instead of this. So what happens is AB times 1 minus cosine gamma over 2 equals. Now, I will express the half of the perimeter with whatever the definition actually is. So P minus A would be minus A, which means minus 2A. It would be minus A plus 2. So it would be minus A plus B plus C over 2. Now, if it's P minus B, it would be A minus B plus C over 2. All right? If it's minus B, and I'm using the common denominator 2, it would be minus 2B, so it's right, exactly. All right, now, so what we can do is we can multiply everything by 4, right? So we will get rid of the denominator. So on the top I will have, so if I multiply by 4 and this is 2, so I still have 2 here, so it's 2AB times 1 minus cosine. So I will multiply it separately. Gamma equals. Now this, I don't have any denominators anymore, right? So what is this? It's C, okay, it's C plus A minus B, which is this, and C minus A minus B, which is this, right? This is C plus A plus B, and this is C minus A plus B. Why did I do it? Because it's easier for me. Right now it's, remember, x minus y, x plus y, it's x squared minus y squared, right? So x is C, and y is A minus B. So my right part, 2AB minus 2AB cosine gamma equals, my right part is C squared minus A minus B squared. Or I can open up this square and I will have what? A squared minus 2AB plus B squared, right? And everything with a minus sign. So I will have minus A squared, now plus 2AB and minus B squared, right? So what's left? Well, 2AB is immediately out, and I have, if I will bring A squared and B squared to the left by adding this to both sides, I will have A squared plus B squared minus 2AB cosine gamma equals C squared. Now, what is this? Well, you have to recognize this. This is a law of cosine, right? This is the law of cosines. And I did present this law in one of the previous lectures about trigonometric identities. So this is a true statement. So from this, using these transformations, we came to this. This is true. Does it mean that this is true? Well, not exactly. What we have to do really is to say this very important phrase. Since all transformations are reversible, they're all invariant transformations. We didn't lose anything, we didn't add anything. This is all invariant and reversible transformation. So from here I can go to here, to here, to here, and here. And that's the proof, because from true statement we came to this one. And that's the end of the proof. Okay, next. Actually, it's very similar. AB times cosine square of gamma over 2 equals P minus C, where again A and B and C are sides, P is half a perimeter, and gamma is an angle which is opposite to C side. Now, again, I will do exactly the same in the beginning. I don't like the cosine square of gamma over 2. I would like to convert it into the first power of something. So how can it be done? Well, again, let's remember cosine of 2 phi is equal to cosine square phi minus sine square phi, right? That's the only thing which I remember. Everything else I derive. Now I will express sine as 1 minus cosine. So what I will have is minus, so it will be cosine square phi minus 1 plus cosine square phi, which is 2 cosine square phi minus 1, from which we conclude that cosine square phi is equal to 1 plus cosine 2 phi over 2, right? And that's what I'm going to use here. So phi would be gamma over 2, 2 phi would be gamma. So my next formula is this. AB times 1 plus cosine gamma over 2 equals, and again from the formula for P is A plus B plus C over 2, and if I will subtract C from this, it would be A plus B minus C over 2, right? So I have to prove that. Again, multiplied by 4, so this would be 2, so it's 2AB plus 2AB cosine gamma, and here it's A plus B plus C, and sorry, it's A plus B plus C and A plus B minus C, right? So it's A plus B square minus C square, right? It's A plus B square minus C square. So 2AB plus 2AB cosine gamma equals A square plus 2AB plus B square minus C square. 2AB goes out. I add C square to this, and I subtract 2AB cosine to there, and I will get C square equals to A square plus B square minus 2AB cosine gamma, which is exactly the same law of cosine, and this is a true statement for any triangle. And from this we can reverse all these transformations to get to this, and that's the end of the proof. So in both cases we were using some simple transformation, actually two different transformations. We expressed sine square or cosine square of half of gamma with the cosine of gamma. That's number one. So we were using basically the formula for a cosine of double angle. And the second transformation was the law of cosines. Right? Okay, next. Next, we are going to prove the following formula. S, which is the area of a triangle, equals to 1/4 of A square cotangent alpha plus B square cotangent beta plus C square cotangent gamma. We have to prove this formula. Well, we have many different ways actually to express the area, right? It's, let's say, a side times an altitude which falls onto this side divided by 2. Or we had some formula which I proved in the previous lecture about using the radius of the circumscribed circle. Another formula for area of triangle was the Heron's formula, which I have derived long time ago in the geometry chapter, which was dedicated to the area of triangle. So this is yet another formula for the area of a triangle. So we express the area in terms of sides and angles. Okay, let's prove it. Let's circumscribe a circle around our triangle. Okay. Now, this is a perpendicular from the center onto this side, and this is the radius. Now, this is R. Now, this is B, so this is B over 2 and this is B over 2, right? You remember that the perpendicular in the isosceles triangle to the base is actually not only the altitude but also median and the bisector of the angle. Now the AOC angle is a central angle supported by this arc. ABC, which is beta, is an inscribed angle supported by the same arc, and we know that the central angle twice as big as the corresponding inscribed angle if they are supported by the same arc, and this is half of the central angle, so this is also beta and this is beta. Now let's consider this particular triangle. Let's say this is D. Triangle AOD. What do we know about this triangle? This is a right triangle. This is AG is one catetus and OG is another catetus, right? Now, AG is equal to B over 2. OG is equal to, well, think about it this way. If you divide OG by AG, OG by AG, this is a cotangent of beta, of this angle, right? From which we can conclude that OG is equal to AG, which is B over 2, times cotangent beta. So the area of this triangle, the area of triangle AOD is equal to one catetus, which is AD, B2, times another catetus, which is B squared over 4 and cotangent beta. Now, exactly the same way, if we draw this, we can have that area of AOB, triangle AOB, is equal to, this is C and this is A, right? So this would be C squared over 4 cotangent gamma. And area of BOC is equal to A squared over 4 cotangent alpha. And obviously if you add all these together, you will get this formula. All right? So what did we use here? Well, we used a couple of geometric properties, like for instance that inscribed angle is half of the corresponding central angle if they are supported by the same arc. Then we were using the property of isosceles triangle AOC, And by the way, it's isosceles because AO is a radius and OC is a radius, right? O is the center. So in this isosceles triangle, the altitude is the same as median and angle bisector. And that's what actually made triangle AOD simultaneously the right triangle and the one which has this angle equals to beta. Everything else is basically a definition of a cotangent and area. Everything else was simple. Okay, and I have the last problem. Prove that R is a radius of circumscribed circle times HA times HB times HC. These are three altitudes correspondingly towards side A, B, and C equals to A square, B square, C square. So we have to prove that this is true for any triangle. Okay. Now, let me draw exactly the same picture as before. Now, this is angle beta, and this, as we have concluded, is angle beta as well. Now, this is its opposite to B, so this is B over 2, and this is B over 2. And this is R. So R is equal to, well, let's think about it. B over 2 divided by R is a sine of beta, right? So R is equal to B over 2 divided by sine of beta, right? Which is exactly similar to if I will use this or this, I will have R from this particular triangle equal to C over 2 sine of gamma, and in this particular triangle, very similar. So this is alpha, now this is alpha, and this is gamma, equals to A over 2 sine alpha, right? So this is simple. This is again from this drawing, it's kind of obvious, and we were using this many times before. Now, using this, instead of R cube, the first R from the R cube I will replace with this, the second with this, and the third with this. So what will I have? I will have A, B, C divided by sine A alpha, sine beta, and sine gamma. 2 by 2 by 2, it will be 8, and this 8, it will be 1, it will be reduced, times HA times HB times HC. So that's what I will have on the left. So instead of R cubed, I put, this is R, this is another R, and this is the third R. This would gives me ABC on the top, and the product of sines on the bottom, and the 2 by 2 by 2 and this 8 will be reduced to 1, and I have to prove this. Or this. Or this, right? So far everything is equivalent, reversible, so instead of proving this, I will prove this. let me just draw another picture where it would become kind of obvious. If you have a triangle A, B, C, this is HA, now this is gamma, alpha, beta. Now HA, this is angle beta. So if I divide HA by C, I will have a sine of beta, right? This is an opposite catetus. So HA is equal to C times sine beta. Okay. How about HB? Okay. HB is A times sine gamma. Right? HB divided by A is a sine of gamma. So HB is equal to A times sine of gamma. Great. And the last one. This is HC. B times sine of alpha, right? Because HC divided by B would be the sine of gamma. So it's B sine of gamma, sine of alpha. Sorry. And if you multiply these three, you will get this. End of story. Well, these are three relatively simple problems, and what I recommend you to do is just by yourself go through all these 4 problems and try to do it yourself again after you have listened to this lecture, just to make sure that you remember everything and it's fresh, etc. And by all means, don't hesitate to sign in as a student to unizor.com, have somebody else or maybe yourself under a different name sign in as a supervisor, and make sure that you are enrolled in some course, and then you can take exams. You can take as many times as you want. Everything is completely free and no checking is done. So just verify whether you are mastering this material. So thanks very much. That's it for today. Good luck. Hi, I'm Zor. Welcome to Unizor Education. Let me continue talking about trigonometric aspects of geometry. So I'm going to solve some geometric problems using the trigonometry. Well, in this particular case, I'm not attempting to solve like any problem. However, it probably can be categorized as a nice illustration of geometric property using the trigonometry. I will be talking about the lengths of circumference of the circle and the area. And we know the formulas, right? So the circumference is 2 pi r, where r is the radius, and the area is pi r squared. Now, I would like to approach these particular formulas from trigonometric aspects which we know. And again, I'm not really pretending that I'm going to prove or solve something. It's more of an illustration. Now, in one of the previous lectures, the one which was about trigonometric inequalities, I have derived this inequality between sines and tangents and the arguments in radians. Now, this formula was actually based on certain geometric properties, and that's why it wouldn't be correct to derive geometric properties from the formula. However, as an illustration of this particular fact, which just proves that there is no like internal contradiction in the theory, I would like, based on this particular inequality as given, I would like to derive these formulas for the circumference and the area of a circle. Now, to do that, I have to basically define what is the circumference and what is the area. And now, these aspects were actually touched in the geometry lectures of this particular course. So I do recommend you to review lengths and area in the geometry course, and also we will need some information from the limits theory, and these aspects I also presented in the algebra course in one of the lectures. It's called basically sequences and limits. So please familiarize yourself with these particular topics before we go any further. And again, what I am trying to accomplish here is to derive these formulas using this particular trigonometric inequality. Now, all right, so let's start with, let's say, the circumference. By the way, this particular trigonometric inequality implies very simply the following. Now, for x equals to 0, obviously these are all equal, so I can say that x is greater than 0 and less than pi over 2. I mean, that was the condition of the original, but it's enough actually for us to concentrate on these particular angles. Now, it's very easy to derive from here. If we divide by x, I will have sine of x over x less than 1 from this one, right? Now, if I divide this by x, I will have 1 less than, and instead of tangent, I will put sine of x over cosine of x and x, right? Or 1 over cosine of x, sine x over x, right? So, what do I have here? If I will multiply it by cosine, both sides, I will have the cosine of x less than sine of x over x. And combined with this, I have this, right? Now, obviously, as x becomes smaller and smaller, this thing becomes closer and closer to cosine of 0, which is 1. Now, this is the 1 as a constant, so these two are narrowing and narrowing the interval where sine of x over x can actually be, and it's narrowing to 1, which means that the limit of that thing is equal to 1 whenever x is going to 0, right? So let's just have this on a side, and I will put it here, that limit of sine of x over x is equal to 1 as x goes to 0. Alright, so we'll keep it in mind. Now let's talk about circumference. There is no like direct definition of what is the circumference of a circle. It's more of a definition using the limit theory. So if you have a circle, and let's say you inscribe some polygon into this circle, and then you increase the number of sides of this polygon in such a way that the maximum side, like in this particular case, is diminishing all the time down to zero. So if you have this process, and for instance, how you can accomplish this process? Well, you can always define a new polygon by dividing each side in two and replacing old polygon with new one, like this. This would cause every side to be smaller and smaller and smaller. Now, as this process continues infinitely, so the sides of the polygons are getting smaller and smaller down to zero, then we can say that the limit of this process is the circumference. Now, obviously, you have to prove the existence of this limit and the uniqueness of this limit, regardless of how you arrange this process of inscribing polygons into a circle. So these are very interesting aspects of the whole theory of the circumference or length of any curve, basically. And it's beyond the scope of this course. So I will just state that if this process is arranged in such a way that the length of the biggest segment is going down to zero, then there is a limit. It's a unique limit regardless of the process, and this limit is called the circumference. So I will use this particular definition of the circumference, and here is what I'm going to do right now. So let's say I would like to know what's the limit of my circumference. So I would like to basically derive this formula using these trigonometric inequalities. So let's say I have some kind of a polygon inscribed. In this case, it's a square, and now in this particular case, the number of sides is, let's say, n. Now on this particular drawing, n is equal to 4. Now, and let's consider this to be a regular polygon with n sides inscribed into a circle. Now, regular polygon is the one which has all the sides equal and all the angles are equal. So in this case, all the angles are 90 degrees and all the sides are equal because it's a square. Now, what exactly is this particular segment AC in this case? Well, what is this angle? Now, if my entire angle is 2 pi, right, 2 pi radians, and again, why the entire angle is 2 pi radians? 2 pi radians? Because we have defined the radian as an angle supported by the arc which has the length of r. So basically, I'm implying that if I use the entire circle, which is 2 pi, it's obviously 2 pi. The circumference should be 2 pi radians because I have to divide the whole circumference into this to get the number of radians to get the 2 pi, right? So I'm kind of trying to prove something which I already know. But again, I'm saying it's not really a proof, it's illustration. So let's just relate to this as an illustration that the theory doesn't have any internal contradictions. All right, so now the angle AOB, is 1/n of the entire circle, right? Since this is my n-sided regular polygon, then this particular angle AOB is 1/n because it's supported by one side. Now the angle AOC therefore is equal to half of this, right? Because these are two radiuses. This is the altitude of the triangle AOB. So it's pi over n. So this is pi over n. This is angle. Now, OA is radius, so AC is equal to R times sine of pi over n. And therefore AB, which is the side, is equal to 2R sine pi over n. And therefore the perimeter of the entire n-sided polygon is equal to n times side, which is 2R n sine pi over n. So that's my perimeter. So what I was saying was that if I inscribe regular polygons one after another with increasing number of sides, let's say I divide each side in two, like from 4 sides, from square I go to 8 sides, then to 16 sides, etc. That will reduce this length of each side. So what's the limit of this? What's the limit of 2Rn sine of pi over n as n goes to infinity? Well, we can say it slightly differently. 2r, that's the multiplier, and limit doesn't really depend on it. Then limit. Then I will have sine of pi over n divided by pi over n. Now, as n equals to infinity. Now, I have this pi, it's an extra pi, so I have to multiply by pi to neutralize it, right? So sine of pi over n divided by pi over n and multiply by pi, that would be exactly n sine of pi over n, right? N goes to numerator and pi will be reduced, so that's exactly what it is. Now, this is exactly the same as limit of sine x divided by x as x goes to 0, where x is pi over n, right? If n goes to infinity, pi over n goes to 0. So I can just say it this way, right? Which means that the entire thing has 2 pi r as a limit, because this is 1. And that's what I actually wanted to derive, this same formula, which again, it's not like I don't know it. I know from the definition, basically, of the radian and some geometric properties. But still, it's interesting to illustrate the connection between trigonometry and geometry, which we already know. Now, the second part would be about the area, and it will be very, very similar, actually. So let's talk about area. Again, let's inscribe a square. Doesn't really matter what kind of. Okay, so again, the area of a circle would be a limit of the area of polygons inscribed into a circle, and the process would be exactly the same, that the number of sides goes to infinity and the length of each side of the polygon goes to 0. So let's just assume that we start with this particular thing, and this is, again, n is equal to 4. It's four-sided polygon, and we're talking about regular polygons because it doesn't really matter which polygons we are inscribing. There is a theory which shows that it doesn't really matter what's the kind of polygons you're inscribing, as long as the length of the biggest side goes to 0. All right, now, so we have to approximate the area of this sector with area of this triangle, because as the number of sides increasing, the triangle AOB would be closer and closer to a sector AOB, and that's why the area of the rectangle. So what we have to calculate right now is the area of this square, and based on the n, and then n goes to infinity, and we will see how it goes. Now the same considerations. So this is r. This is, as we already know, p over n. So AC is equal to r sine of pi over n, right? Now OC, which is an altitude, is r cosine pi over n. Okay? Now, so AC is half of the base. Now OC is the altitude in this triangle, and therefore the area is equal to the product of these two things, right? So the area is r squared sine pi over n cosine pi over n. Or if you wish, it's 1/2 r squared sine 2 pi n over n, right? Remember, sine of double angle is 2 sine of single angle times cosine of single angle. So the angle is pi over n. So 2 pi over n, if I would take the sine, it will be 2 sine pi over n and cosine pi over n. And I have 1/2, and that's why it goes this way. So the area of the entire polygon would be n times greater, right? So right now I have only one side. Now I have all n sides. So the area would be n times r squared times 1/2 times sine of 2 pi over n. And since I would like, actually, instead of n going to infinity, have some kind of x going to 0, where x probably should be 2 pi over n in this particular case, right? So this would be equal to 1/2 r squared. Now sine 2 pi over n divided by 2 pi over n. And I have to neutralize pi and 2. So I have to multiply it by 2 pi, right? Right. And now, what's the limit of that thing? Now, this is the variable which depends on this x, which goes to 0, which means the limit is 1. So I have 1/2 r squared, 2 and pi. So the limit is pi r squared, which is the area of the circle. So again, my purpose was to illustrate that there are no contradiction between the geometry and trigonometry, and obviously there should be none. But I think it's a nice exercise of how to basically bridge these two things together. None of this is actually a proof of the circumference length or the area of a circle, but it's just an illustration or explanation, whatever you want to treat it, of the validity of all these formulas, that they're all connected somewhere. And it's probably quite an interesting phenomenon. You learn something, and then you learn something else, and all of a sudden you see that somewhere there is a connection between these things. And the more you know, the more connections you will see. So this is just one of the connections which I wanted to illustrate. Okay, thanks very much, and good luck. Hi, I'm Zor. Welcome to Zor Education. I would like to solve a few trigonometric problems related to geometry. Basically a continuation of the topic. Obviously, as usually, I do recommend you to try to solve these problems yourself first, because that's the whole purpose. So you will be actually solving the problems, and only then listen to this lecture. So if you didn't do it yet, just press the pause button and try to engage yourself into thinking about these problems. Okay, so let's not do anything and let's go straight to the problems. Okay, problem number 1. If you have a triangle vertices are ABC, angles are alpha, beta, gamma, and three altitudes. The altitudes are HA because it falls on the side A, which is this one. This is B, opposite to the vertex B, and this is HB. And this is HC, falls to the side C. So, any triangle, and I would like to prove the following property. HA times sine of alpha equals HB sine beta equals HC sine gamma. Well, all problems today will be relatively simple. Now, looking at that, I don't know, it reminds me immediately the law of sines. So something should be related to the law of sines. Now, what is the law of sines? It's A over sine alpha equals B over sine beta equals C over sine gamma, right? At the same time, we know that A times the altitude, which is falling to A, it's the same as BHB, the same as CHC. This is double area of the triangle, right? The base times altitude divided by 2, or the base times altitude divided by 2, or this base times altitude divided by 2. So all these are areas. So side times the altitude towards this side is double area. Now, from these two, I can very easily derive this one. How? Well, for instance, HA equals 2s divided by A, HB is equal to 2s divided by B, and HC is equal to 2s divided by C. And if I will substitute in this, I will have exactly the law of sines with the multiplier s everywhere, right? So I will have, so since HA is 2s divided by A, I have this, right? Now this is 2s over A sine B, and this is 2s over B sine gamma. Now, these are equal, right? Because s is just a multiplier everywhere, and this is the revert reverted or reversed, whatever, inverted law of sines. So law of sines is A divided by sine of alpha equals to, this is B, I'm sorry, and this is C. So this is inverted law of sines, basically, because law of sine is A divided by sine of alpha, B divided by sine of beta, and C divided by sine of gamma, and this is just inverted. So if these are equal, then inverted are equal as well. So this is basically the proof. We start from the law of sines, we can invert it, multiply by 2s, and we got this one. So everything is like reversible in both the directions. Okay, that's it for number 1. Number 2. Given a parallelogram with acute angle alpha, we have to prove that 4 times AB times AD times cosine alpha equals to AC square minus BD square. Now, AC square is a diagonal, BD is another diagonal. So the difference of squares of diagonals, the bigger minus smaller. It's 4 times AB times AD and cosine. Well, whenever you see something like product of two sides and the cosine between them, of the angle between them, that actually reminds the law of cosines, right? Now, what is the law of cosines? Applicable to triangle ABD, law of cosines is, well, let me just call this thing, I will call, let's say, P, this thing I will call Q, just to make it easier, right? So AB is P and this is Q, all right? This is X and this is Y, X, Y. So from the triangle ABD, y square equals p square plus q square minus 2pq cosine alpha, right? That's the law of cosines. Now, from triangle ABC, x square equals p square. Now this is parallelogram, which means this is also q, right? So p squared plus q squared minus 2pq cosine, and what is this angle? Well, this angle is pi minus alpha, right? 180 degree minus alpha. So this is pi minus alpha. Now, by the way, cosine of pi minus alpha equals to what? Cosine is abscissa, right? So if this is the unit circle, this is alpha, this is pi minus alpha. Abscissa is the same by absolute value, but with a minus sign. So it's minus cosine alpha. So that's why this is equal to p squared plus q squared plus 2pq cosine of alpha. Right? Now, what is AC square minus BD square, x square minus y square? If I will subtract from this, p square will be reduced, q square will be reduced. This is plus 2pq cosine, and this is minus, but I'm subtracting, so it will be plus. So it will be 2pq cosine minus 2pq, which is 4pq cosine of alpha. That's exactly what this is. That's it. Very simple problem. By the way, for the previous two previous problems, the first one contains sines, and it kind of implied that the law of sines should be applicable. And the second one contains the product of two sides by the cosine of the angle between them. And again, this prompts for law of cosines. And indeed, in both cases, these two theorems did help. Okay, now, let's say you have any triangle so this is A, this is B, and this is angle bisector. So these two angles are the same, and each one is equal to gamma over 2, right? Since it's a bisector, this is angle gamma, and this is LC, right? The bisector. Now, we have to prove that LC times A plus B equals 2AB cosine gamma over 2. So bisector times sum of the sides in between them, this bisector actually goes, is equal to 2AB in cosine. All right. Now, actually, I'm sure there are more than one way to prove this particular equality. The one which I have chosen is, let's just have these two perpendiculars as altitudes of triangles ADC and BDC. And what I will do is, I will compare some of the areas of these two triangles with the area of an entire triangle. Now, what is the area of ADC in terms of the base and an altitude? Well, the base is B. Altitude from this triangle DCM. It's a right triangle. Hypotenuse is LC. The acute angle is gamma over 2. So I know the DM, the altitude, in this triangle, and it's a cagetus in the right triangle DMC. It's equal to hypotenuse times sine of gamma over 2. So my area of triangle ACD equals ACD equals B times altitude, which is LC times sine of gamma over 2, and divided by 2, right? Now, area of triangle BCD equals, again, 1/2 of the base, which is A, times LC, times DN is exactly the same. It's also LC times sine of gamma over 2. On the other hand, the area of triangle ABC, the entire triangle, is, let's think. Well, if I will take this particular altitude, so it would be B, 1/2 B, and this particular altitude is A times sine of the gamma, right? From the triangle BPC, BP is the catetus, BC is hypotenuse, length of A, and the angle is gamma, so the opposite catetus. Now, sum of these two is equal to this, right? Well, therefore, well, let's just forget about 1/2. If I will sum these two, I will get LC times A plus B sine of gamma over 2, right? If I will sum these two, and I'll drop 1/2 because it's reduced, it will be reduced anyway. And on the right side, I have this. Well, they are close to this one, but just need a little bit more. Now, obviously, sine of gamma, it's 2 of gamma over 2, right? So it's gamma over 2 plus gamma over 2, double gamma over 2. So it's 2AB sine gamma over 2 and cosine gamma over 2, right? That's what sine of gamma is. It's 2 sine gamma over 2 cosine gamma over 2. I still remember the formula for the sine and the cosine of the sum of two angles, right? So this is gamma over 2 plus gamma over 2, that's what it is. And from here, obviously, we can reduce by sine of gamma over 2, and we get exactly this. That's it. Now, what was interesting about this particular problem? I was using additional construction. I put all the altitudes and the concept of area. I don't know what exactly prompted me to do this. However, we do have to include this bisector LC into some kind of a equality, right, from which we can derive the equality which we need. And, you know, sum of two areas of the small triangle is equal to the area of the big triangle is really an equality. And I'm sure there are some other components of this triangle which can be connected together with some kind of an equation. Well, again, the problem can have many different solutions. This is just one of them, and it seems to me it's relatively simple, because all I need to know is that the catetus is equal to hypotenuse times the sine of the angle or something. All right, next. Next we have an isosceles triangle ABC, and we have altitudes. One altitude, another altitude, and another altitude. So these are right angles. Now, this angle is given. Let's call it gamma. So gamma is given. Now, what I have to find out is Now h is the intersection of these three altitudes. It's called orthocenter, by the way, of the triangle. I have to find out in what ratio point H divides the altitude from C to F. So basically I have to find out the ratio HF divided by CH. All right? Now, it's actually quite easy. First of all, this is a isosceles triangle, right? So this altitude is everything. It's altitude, it's angle bisector, it's median of this side, and it's basically the axis of symmetry, right? The whole picture is completely symmetrical because this is perpendicular, so and CD is equal to DB, so point C and point B are symmetrical relatively to this one, so everything is symmetrical. So it's very easy to prove, for instance, that EH and HF are exactly the same. Well, why? Well, for instance, you can consider right triangles AEH and AFH. They have the common hypotenuse, and the angles are the same because the altitude is a bisector, angle bisector as well, right? So everything is symmetrical. But now let's think about it. Angle EHC. Consider angle EHC. Well, this line is perpendicular to this. This line is perpendicular to this. So basically, this angle is the same as this angle, right? Because it's two angles which are formed by mutually perpendicular lines. Now, from this we can obviously, and this is equal to, well, this is alpha, so this is alpha. So from this we can see that angle ECH ECH, right? Is equal, basically, pi over 2 minus alpha, because triangle CHE is the right triangle. Now, I just mentioned that EH is equal to HF. This is equal to this, because these triangles are congruent, right? So basically, if you consider right now triangle ECH, it's the right triangle. The angle alpha is something which we definitely know. So what is the ratio of HF to CH? It's the same as EH to CH, right? And this is, by definition, a cosine of alpha, right? That's basically EH over CH, which is the same as HF over CH. So this is what we actually need. The fact that this angle is perpendicular this and this, so this angle is equal to this one. That's sufficient to basically say that the ratio between segments into which point h divides this altitude is the same as cosine of alpha. So as long as one of the angles is given to us, if this angle is given, then we can obviously calculate what this one is, because this is an isosceles triangle. So as soon as we know one of the angles of the isosceles triangle, we know this angle on the top, and the cosine of this angle on the top is the ratio which we need. Well, that's it. Next, given a rhombus, now this is point M, and it's chosen in such a way that area of triangle ADM, this triangle, is equal to 1/3 of the area of an entire parallelogram ABCD. Now, what's also known is that the cosine of alpha is equal to 1/4. What we have to prove is that AM divided by BM equals 2. This would have to be proven. So knowing that the area of this triangle is 1/3 of the area of an entire parallelogram, and knowing that the cosine of this angle is 1/4, we have to prove that the AM is twice as big as BM. Okay? All right. So what I'm going to do is I will put some abbreviations. Let's say this is A, this is X, this is Y. All right. Now, what I will also do, since we are dealing with areas, I will need altitudes. So this is one altitude, MP, and this is another altitude, BQ. Let's say this is equal to U and this is equal to V. Right? So MP equals to U and BQ equals to V. All right, now let's do the calculation of the areas, right? Now, the area of the parallelogram is base, which is A, times height, which is V. So here I have A times V. Or, if you wish, this is a rhombus, right? So all sides are A. And knowing the cosine of this angle, I can very easily find the altitude BQ, right? That's A times sine of alpha. But let's just leave it for later. Now, the area of a triangle is equal to base, which is also A, times altitude. So this is equal to A times U, but it's a triangle, so we have to divide it by 2, right? Let me wipe out this, so it doesn't really bother us. And we know this. Now, this is angle alpha and this is angle alpha. Right? Because this is a rhombus, which is therefore parallelogram, so these are parallel. Now, knowing x, I can calculate the altitude here as well. So, this particular equation would look like this. A times, instead of u, I will put x sine alpha. X sine alpha divided by 2, right? And on the right I have 1/3 A times, and instead of V I will put A times sine alpha. So from here I immediately see that x is equal to 2/3 of A. That's interesting, right? Such a complicated calculations and conditions related to area, etc., and it looks like x is equal to 2/3 of A even without the angle alpha. It's independently. So for any angle alpha, that would be the case. So if I draw the line which cuts off the triangle, which area is 1/3 of the area of the rhombus, then this particular piece would be 2/3 of the side. All right, but we don't need really this. We need the ratio between AM and MD, right? So in this case, since I already know this x, I can find out AM, which is y, using the law of cosines, right? So law of cosines says that y squared is equal to a squared plus x squared minus 2ax, and the cosine. Now what is this angle? This angle is pi minus alpha, right? Or a squared plus x squared is 4/9 of a squared minus 2ax is 2/3 of a, so I put squared here. Now the cosine of pi minus alpha we already spoken during this lecture. It's negative cosine of alpha, so I'll put this plus and cosine of alpha. But luckily we know what is the cosine of alpha. It's 1/4, right? So this would be a squared plus 4/9 a squared plus. This is 1/4. This is 2 times 2, which is 4. So it will be reduced. So I have a squared divided by 3. Okay, x is equal to 2/3 of 8, that's what we have found. And this is what? The common denominator is 9, so this is 9, plus 4, 13, plus 3, which is 16, So it's equal to 16 ninths a square.